Uh, mm, Hello guys. Today I'm going to present group pose, simple baseline for end-to-end multi-person pose estimation, published in ICCV 2023. Uh, so the contribution of this paper is very simple. They propose a simple yet effective state-of-the-art transformer approach for multi-person pose estimation. As you can see from this figure, group pose compared to the previous existing architectures is much more simpler. For example, in PETR, we have two modules, pose decoder and the joint decoder. Or in ED pose, we have also two modules, the human detection decoder and human to key point detection decoder. But unlike any of these, group pose is simply a transformer decoder, and that's all. Uh, so that's what they are promising, the simplicity of this approach. And it goes through about the overview, and the model architecture is also very simple. So we have a backbone which directly follows DTR frameworks to be the backbone transformer encoder. So we have 6 deformable encoder transformer layers, and they use 4 feature levels with downsampling of rates of 8, 16, 32, 64. As you can see, it's very simple encoder and backbone. Um, Next is decoder. Uh, the decoder adopts a bit different from previous approaches. It adopts a combination of n multiplied by k key point queries, where k stands for the number of joins and n stands for the number of instances, and another n instance queries to predict and score one pose. And the key point queries, you got each key point as an object and are used to regress n multiplied by k key point positions, while each instance query is for scoring the corresponding k key point pose prediction. And it's simply a consist of 6 same decoder layers, and it also follows the same macro design of previous DTR frameworks, and it builds in self-attention, cross-attention, is deformed by attention, and FFN. But there's a slight difference between the previous approach and this approach. Their self-attention is slightly different from the previous approaches. And next is prediction heads. We have 2 prediction heads implemented with fast-forward networks. One head is for human classification, and the other head is for human key point regression, and it predicts for n human poses. Each contains a classification score and a k key point positions for corresponding k key point pose. So you have one score that defines a probability of a human in that position, and the rest is the key point position, the joint positions for this guy, and so on. And next, we have a loss function. It's also simple. They employ a Hungarian matching algorithm for one-to-one assignment, as same as in DTR frameworks. And it consists of simply 2 losses: a classification loss, as we know, a cosentropy loss, and maybe in this case, binary cosentropy loss, and a key point regression loss. It's a simple combination of L1 loss and object key point similarity loss. And now we come to the queries. That's where they stand out from previous DTR frameworks. So it proposed 2 types of queries. The key point queries is constructing the content part of k key point queries in dimension of k multiplied by d, which is d is the hidden dimension in each human instance by combining k randomly initialized learnable key point embeddings, which is also same size, and the corresponding output memory feature, 1 minus d, 1 multiplied by d, and the position part of k key point queries also in each human instance is initialized with corresponding predicted k key point pose. And then we have instance queries, which constants on the content part by using a random initialized learnable instance embeddings, because since we use this instance query for classification task, we do not require explicit position information. And then performing cross attention in the decoder layers, the mean of k key point positions are used as the reference point for the instance query in this human instance. So this cross attention is a deformable attention, so they need some kind of reference point, and they use the k key point positions, the mean of k key point positions as a reference point. And now they propose the self-attention. They have different kinds of self-attention. So a standard self-attention, if we had standard self-attention, it's simply self-attention between all queries, which is n multiplied by k plus 1 multiplied by n multiplied by k plus 1. And we can have also same attention with mask, so we do self-attention only the same kind. This is also not so effective as they claim. So, but what they propose is different. They have two types of self-attentions, n within instance self-attentions. So it calculates n self-attention maps for n human instances in parallel with shapes of k plus 1 multiplied by k plus 1, so as to exploit kinematic relations and gathering information for scoring post-prediction. So it's inside for each n instance, we perform self-attentions in k k key points. And then we have k plus 1 same type across instance self-attentions. So this case, we calculate k plus 1 self-attention maps with the shapes of n multiplied by n, so that to collect information from same type queries in other instances and help remove duplicated predictions. And now we come to the experiments. The settings are also very simple. They use two commonly used datasets. MS-COCO, CloudPose has MS-COCO has 200k images and 250k person instances with 17 key point annotations per instance, which means the k is 17. And the CloudPose, which has 20k images and 80k person instances with 14 key point annotations per instance, which means k equal to 14. And as an evaluation metric, they use the common evaluation metrics, the OKS, object key point similarity based average precision, as the main metric for both datasets. And the implementation details, they follow the same augmentations as in the DTR frameworks, which are random flip, random crop, random resize with short sides in 480 by 800, and the long side less or equal to 1333. And they train for 60 epochs and 80 epochs and MS-COCO and CloudPose respectively with a batch size of 16, and they use Adam W as an optimizer. And when they test, they input imagery size with the short size being 800 and long size lesser or equal to 1333. And here's the main results. So I will go one by one. First, we have table 1, in which we test our data on MS-COCO validation dataset. And this KR stands for key point regression losses, and HM stands for heat map loss, and BR stands for, I think, box regression loss. As you can see, the group pose is a lot simpler in terms of losses and much better in terms of accuracy. As you can see here, if you use swing L transformer as an backbone, we get the state-of-the-art accuracy compared to others. And now we compare on MS-COCO test dataset, and their notations are same as in this one. And we can see from results again, if we use the bigger transformer as a backbone, we have 72.8 AP compared to others. And then we are also compared with CrowdPose test dataset, and we can see from results that by using this SwinL, we have state-of-the-art results compared to previous methods. And now we come to ablation experiments for group pose. We have several types of ablations. First of all, the query designs for human instances. So they consider only instance query types or only key point query types or all of them together. And we find that if we use both of them, and we have the best AP score. And then they find out the benefits of instance query. And as we can see from results, that if we have instance queries, the AP score increases. Then they find out how many instances required for this model to work best. And they found out that the 100 is considered the best, because if they use more, then the accuracy does not improve at all. Then they find out this self-attention implementations. I want to know what happens if they use only standard self-attention or group self-attentions. And you can see here the standard self-attentions, group self-attentions performs better than standard self-attention mechanisms. And they also find out what happens if we disable one of those self-attentions, such as vision instance self-attention or across instance self-attentions. And we can see if we use both of them, we have better AP. And they also consider the inference speed. They test their model on 800 GPU. And we can see that the time is much faster than the previous methods, 15 milliseconds and 32 accordingly. And the FPS is also real time compared to previous approaches. Yeah, that's all from me. Thank you.